Good morning all. I've waited a long time for this thing to arrive, about 6 weeks I think it took for this thing to be shipped to me. So let's open it up because I'm very keen to play with it. I think it's just that bit there. Yes, it is a pair of integrated circuits. So these are MC14495 CMOS integrated circuits. Now, they're not part of the standard 4000 series CMOS. This one looks a bit battered, actually, doesn't it? It's had a bit of damage up at that end. And I believe there was a series called the 4500 series, but these are 4495, so they're a bit of an oddity. Let's take a look at the datasheet. And, well, you can see it's a Motorola semiconductor hexadecimal to 7-segment latch decoder LED driver, but I think I'd probably call it a 4-bit binary to hexadecimal on a 7-segment display latch decoder driver, because what it does is it takes in a 4-bit binary word or nibble. There's a latch which you can enable or disable. Then there's the decoder, which turns the 4 bits of binary into a 7-segment display, but interestingly it includes 0 to 9 and A to F. The other interesting thing that this has is it has these 290 ohm resistors actually within the chip package, so that you can drive a 7-segment LED display directly without having to use resistors between this chip and the display LEDs. So I want to use 2 of these chips on my 8-bit breadboard computer, so that instead of displaying an 8-bit byte in binary on one of these little bar graph displays, we can display it in hexadecimal, 2-digit hexadecimal, on a couple of these 7-segment displays. Now, inevitable questions. Why don't you just use a ROM? Well, this chip is, in a sense, a ROM. It has a ROM section. It's a mask programmed. It's a pre-programmed ROM. And one of the things that I want to do in my 8-bit computer is I don't want any programmable devices. I want it to be all off-the-shelf devices. And this device is off-the-shelf. It's becoming a little bit difficult to obtain, but there are several sellers on eBay who are doing it. So I think it's justified. And bear in mind that this is really just an enhancement to the computer. You can read all the signals in binary on those 8-bit bar graphs. It just will be a little bit easier to read it in decimal, in hexadecimal, on a couple of 7-segment LEDs. So I've seen these for sale from a few different sellers. I think I got these from Polida. They were $1.50 each, so they're not terribly expensive. I'm being a little bit careful because these are sort of old stock chips. They look very nice and shiny and new, but I'm just being careful in case these are a little bit static sensitive, because the old CMOS chips were. Now, my problem today is this. The MC14495 in a typical circuit requires a common cathode LED display. And, well, I bought common-anode, so can I still power this chip up and make it work? So the 7-segment display that I need is a common cathode, which means that it has a bunch of LEDs in like this. I'll just draw 2 of them. And they're commoned at the cathode end. So this chip is going to source current when these outputs are high, current which will then flow through the internal 290 ohm resistor through the LED and down to ground. This will be connected to ground. Now, I don't have a common cathode display. Mine is commoned on the anode side, so I've got a bit of a problem. So my display looks like this. It's commoned on the anode side. So if I draw the 2 LEDs in again, it's commoned here. So here you would typically connect it to VCC or VDD, and then you'd pull these points down to ground individually to light up the LEDs. You'd have to have a current limiting resistor in there as well, of course. So what can I do? How can I drive this type of display from these active high, these high going, these current sourcing outputs? Well, how about this? Each of these I connect to a transistor, an NPN transistor, so that when I put current into the base of that transistor, limited current of course, this transistor turns on and pulls, there would need to be a resistor in there, pulls the cathode of the LED down to ground. Now if I'm going to do this for all 8 LEDs in the 7-segment display, bear in mind of course it has an 8th LED there, which is the decimal point, I'm going to need 8 transistors, 8 current limiting resistors for the LEDs, and potentially additional resistor on the base of the transistor, because these output resistors are 290 ohms. That might be a bit low here because this is designed to drive LED diodes with a forward voltage of about 2 volts, thus leaving about 3 volts across that 290 ohm resistor. Here we're driving it into about half a volt of forward voltage drop, leaving about 4.5 volts across that 290 ohm resistor. It might be all right, but we might need additional base resistors. So what if there were an integrated circuit conveniently filled with 8 transistors with additional base resistors? Well, there is, and it's called the ULN2803. And I'm lucky enough to have a couple of these things. Let's have a closer look at one of them. Here it is, the ULN2803A. Yeah, they're in these anti-static packages, which were just a bit of tin foil glued to a piece of paper. It says it's a static sensitive item, but I'm not sure it can be really, because it's just an array of transistors. These are actually Darlington transistors, so they have very high gain. But this will do the trick, and also it has an integrated base resistor. I think it's 2.7K. So here's a Texas Instruments datasheet for the ULN2803A. Now the logic diagram doesn't show it as Darlington transistor array, it shows it just as inverters with lots and lots of these diodes. Typically these things were used for driving relays or lamps, relatively high current, hence the Darlingtons, loads. And it says here that it has a 2.7K series base resistor for each Darlington pair. Let's go further down the datasheet and look at the internal diagram for each of the 8 elements. So what the chip contains is 8 of these. It's a Darlington pair, NPN. It's essentially open collector. You can pretty much ignore all these diodes because none of them are going to have any effect on what we do. They're there really so that you can drive inductive loads, and any back EMF is clamped by these diodes. But it also has this 2.7K base resistor. Now that's going to be quite useful. The chip, it's the decoder chip, the 14495, has a 290 ohm resistor, but this gives us additional base resistance. This is Darlington, so of course it's very high gain. We should get a very good turn on of the second transistor. And we're only driving LEDs, and we're going to be doing that through additional resistors. So this is just going to behave as an NPN transistor, essentially. So I'm going to build this circuit on this very old breadboard. This breadboard is so old that it has a nice little clip-in LED and pot front panel. Quite nice, these old breadboards. Now this old circuit here was actually a similar decoder, but it's the 7447. This is actually a very old 9357/7447, but essentially it's 74 series logic. But from 1972, I did a video using some very old chips quite a long time ago. I might borrow that set of 8 220 ohm resistors to current limit the current through my... I'm only going to be using a single display, of course, because I'm going to go 4 bits to 8 segments. So I'm going to strip all this stuff off and start building my 4-bit binary to hexadecimal 7-segment LED display. And if you're thinking, well, why don't I just use that 7-segment display? Well, unfortunately, that is also common-anode. The 7447 4-bit binary to decimal, so 0 to 9, this doesn't have the hexadecimal A to F digits. This chip is designed to drive a common-anode display, so that's common-anode, the same as those. And I even found this in a component drawer, which is another common-anode display, a dual 7-segment. But yeah, these are all common-anode, and my chip drives common-cathode. So the first thing to do is check that feeding 5 volts through this little link here to the middle pin on this chip, which is the common anode, and then pulling the cathodes down through a 220 ohm resistor. This just has 8 of them across this package to 0 volts, lights up the segments, and it does those two and those two, and then there are some more down here. So that's fine. Now I'm going to get the ULN2803 positioned here so that it pulls these cathodes down to ground. Right, so the ULN2803, you have to ground pin 9. That's a common ground for all the emitters of the Darlington transistors. All the inputs are on the front edge and all the outputs are on the back edge, conveniently. So if I now tie what is effectively the base of one of these transistors through its 2.7k resistor high, so I don't need a resistor, connect that to VCC, which is up there. Can I find it? Yep. And the collector then pulls through the resistor the cathode of this display down to ground through that link, and so we have a current flow through the LED. So yes, if I do that now for all 8 of the transistors in this package, I can drive all 8 of the LEDs in this display. And what I'm going to do is I'm going to do these in segment sequence. So I'm going to go A, B, C, D with A at the top, B, C, D, E, F, and G as the center bar. H will be the decimal point, so that they're in some sort of logical sequence so that I can remember it. So C might be down there. I can't quite work it out yet. Let's put a third link from the resistor pack over to the Darlington array. That's really the wrong color, isn't it? I want another link. I've got one over here to connect this transistor to positive. Oh, that's H. So where's C? Is it there? Nope. No, it's not the middle one, is it? No, it's there. Okay, that's fine. So I need some more of these yellow ones. Let's create 3 more of these, and then I'll have all 8 of the links between the Darlington array and my blue resistor pack. Right, that's all wired up. So now I can source current from VCC up there into each of these inputs in turn and light up segments A, B, C, D, E, F, G, and H, the decimal point. So now I need to interface the output of my MC14495s to the inputs of these transistors, and that chip can then drive the display. Right, now we need the outputs of the MC14495. 12 goes to A, 13B, 14C, 15D. Right, I've got the 7 outputs because of course I don't need H because that's the decimal point. And I think on this chip the decimal point tells you whether it's in a numeric or an alpha character, so I don't need that. I've got the 7 outputs connected to my 7 Darlingtons, but if I pull the latch enable high, I'm getting a character that doesn't exist, just the sort of top 2 segments, so that's a bit odd. I think the next thing I need to do is put these 4 CMOS inputs to a known state. So what I'm going to do is I'm going to pull them all high with resistors so that I should get an F on the display. So that's what I've done. I've put 4 10k resistors pulling the 4 binary inputs up. So that should most definitely be giving an F symbol. And well, it's not. It's producing this peculiar angle. And if I pull each of these resistors low in turn to get other numbers, I'm just getting rubbish. A back to front L. Well, a 7, but that's the only recognizable character, and that. So I'm just not getting recognizable characters at all. Not sure what's going on here. Right, I've put my little 16-way rotary switch in there. Now I can't remember what the outputs of this is, but I think I found the least significant bit because it's flicking between 2 states as I turn it. So I'll connect that to the least significant bit on the decoder chip. Which one is it? It's got to be A. Yes, A input, so that's pin 5, it's there. Right, so I've got my little rotary switch wired up. I'm pretty sure I've got the correct binary weights to the 4 outputs. And I'm getting some really weird results. 0 displays nothing. 1 is fine. 2, 3, 4, 5 is like a dim version of 3. Really weird. 6, 7 works. 8, 9. That's A, B, C, D, E, F. Now those ones kind of seem mostly alright. A is a dim one. B is kind of B with some segments missing. It looks like A, B, C, D, E and F. No, E and G are missing. Same with C, D, E and F. It's just got segments missing. Why? Back to 0. That doesn't work. And 1. Now there was a funny one. Which one was it? Was it C? That did something really weird. It kind of works one way. If I come back from D to C, I don't get it. If I go from B to C, I do get it. So what's going on here? This is really weird. So just while I try to diagnose this, I've connected up the H output to the decimal point. Now that should come on in all 6 of the alpha characters. So F, E, C, D, and that's C. But that one it doesn't. But it does if I come at it the other way. Or does it? Oh, it's really behaving really weird now. A, that should be on, and it's not on. Now I'm just wondering whether this latch enable, which I've pulled low, whether it's actually edge triggered. I'm treating it as a level triggered thing. So I'm thinking it should be a transparent latch with that pin 7 pulled low, but maybe it's not. It doesn't say much in the data sheet. It just shows it as an inverting input going in, but it doesn't show it as any sort of symbol to show whether it's edge triggered or level triggered. I think I might have to just read the datasheet some more. It's very baffling. Now there is a switching waveform here which sort of hints at latch enable being edge triggered low going, because it's got a sort of a time there after which the output changes state. It doesn't do anything on the high going edge, and then again edge triggered low going, the output changes state again, assuming the inputs change. So maybe latch enable is actually edge triggered. Might need to put a switch on that. Right, I've got a 10k pull up on, you can just about see it in there, on the latch enable, and now if I click the switch, it does seem to be edge triggered, but weird things are happening because I'm getting 1. This is switched to 9. It should be a 9, and sometimes, occasionally, I get a different symbol. So some really bizarre behavior. That's A. That's not showing properly. B, C, D. Let's go back to C. D, E, F. 0. Do you know, I've got a funny feeling that the characters that turn on lots of digits are causing problems, because 1 works, and if I turn this around to 7, 7 works. So is this something where I'm getting a sudden surge of sort of current requirement, and that's crashing this chip, because it is edge triggered, and it does seem to be a bit flaky, and it simply won't display 8, but it's quite happy to display 7. Maybe this is just a power problem, and this chip needs a capacitor simply to provide power through the sort of switching transitions. Maybe that's the issue. And now I've put a tantalum capacitor directly between pins, or what is it, 16 and 8 I think it is, VCC and ground. And no, it's still just behaving very strangely. That should be 5, and it's just doing weird things. 6, 7 is fine. I'm going to change that chip because, well, I've got 2 of them. Right, I've changed the chip to the other chip, and, well, it's fine. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, and the dot comes on. B, C, D, E, F. So what's wrong with that other chip? That's just bizarre. And this is behaving itself completely properly now. 1, 2, 3. And in fact, I can hold the latch enable switch down and just rotate this switch, and it is a transparent latch. So you don't have to worry about edge triggering. 9A, B. B looks very similar to 6. You can see 6 has the top bar and B doesn't have the top bar, but of course because it's an alpha character you get the dot come on. Probably wouldn't display the dot, it's just a bit confusing. You just learn to recognize B. C, D, E, F, and back to 0. Behaving itself completely properly. The other chips are dud. Oh, and I'm actually doing this now with that tantalum capacitor taken out. So yeah, it doesn't seem to be a power related issue or a glitching related issue. Oh, that's interesting. Those do flash, don't they, when you swap them over? That segment top right is flickering even though... Oh, actually, yes, of course, we're switching. It's probably the tracks inside this switch. We very briefly switch to another character. Yeah, that's fine. I can understand that. Yeah, but that works. And it proves the original point that I was trying to make, that we can turn a common anode display into something that behaves like a common cathode display by essentially inverting all the bits through a transistor array. Now, I've ordered some common cathode displays, and when I get them, of course, I won't need to do this little inversion trick. I won't need the transistor array. I won't need these resistors either, because we've got the 290 ohm resistors in the binary to hex chip here, and I'll be able to connect the common cathode display directly to this chip. Now, of course, I will need 2 common cathode displays, because to display 8 bits, you need 2 hexadecimal digits. I'll also need 2 of these MC14495s. Well, as luck would have it, I've ordered 2 more because they were taking so long to arrive that I thought, well, let's just order some more, so they're on their way. So yeah, I guess I'm happy. That all works. Despite Motorola's best efforts to confound me with this dodgy chip, made in 1987, week 48, it would appear. Yeah, that all works. I've got my 16 characters, 6 of them being alphas, A, B, C, D, E, F, all ready to display hexadecimal. So cool. Cheerio.